Today we are going to learn about the G protein coupled receptors. Now your G protein coupled receptors are cell membrane bound receptors. They have 7 alpha helical chain which spans across the cell membrane 1, 2, 3, 4, 5, 6 and 7, and these are arranged into 3 extracellular loops and 3 intracellular loops. These extracellular loops have your drug binding site. And the intracellular loop has your G protein binding site. Now G proteins are heterotrimeric in composition. You see alpha, beta and gamma. So what happens when a drug binds to a G protein coupled receptor? This is your receptor when it is not bound to a drug. Now what is the composition? It is GDP plus alpha, beta and gamma. What happened when a drug bound to this G protein coupled receptor? The GDP changes to GTP and it is alpha, beta and gamma. So what change did this binding of GTP bring to the receptor? Now you see, our alpha subunit likes GTP very much. So it dissociates from your beta and gamma and goes away with GTP. So you are left with GTP alpha and beta gamma subunits. GTP alpha subunit is very active and it either leads to activation of your effector or it inhibits your effector and brings about the biological effect that a drug is intended to give. Now the beta gamma is watching this from afar and says, well, alpha, you are active, let us do some action of our own. So what it does is, it goes and activates your membrane potassium channels. Now potassium concentration within the cell is higher than that outside the cell. So potassium moves out through this channel. As the potassium moves out of this channel, it inhibits the opening of your voltage gated calcium channels. This will not open. So what effect does this have? This will lead to your G protein coupled receptor desensitization. Well, I guess beta and gamma were better after all. Alpha sees this and says, I guess there is no use staying with GTP any longer. So what it does is, it hydrolyzes GTP back to GDP and joins the trio to form your alpha, beta and gamma. So it goes back to this state. But before it does this, it has already activated your effector. Now what can this effector be? Effector can be your adenylyl cyclase. It can be phospholipase C. Now based on your effector, your GPCRs are labeled into various subtypes. Now your G protein coupled receptor can be G stimulatory, which is denoted by S, or it can be G inhibitory, which is denoted by I. So in G stimulatory, your GTP alpha unit will go and activate adenylyl cyclase. Now adenylyl cyclase converts ATP to cyclic AMP. This cyclic AMP will go and activate your protein kinase A. Why is this important? Now your protein kinase A phosphorylates your enzymes or your transporters, your proteins. This phosphorylation of your enzyme can have various effects. It can either activate your enzyme or it can inhibit your enzyme and ultimately lead to the biological effect. Let's study some examples. Let's look at the effect of G stimulatory on this human. Pardon my poor diagram. This will lead to increased contractility of the heart, and it will also lead to glycogenolysis, lipolysis. So it will increase the blood sugar level. This will be easy to appreciate if you see the receptors which act through your G stimulatory effect. One of them is your beta receptor. Now beta receptors function on the heart, as we know, is to increase its contractility. And this effect is brought about by glucagon receptors. Glucagon, as we know, phosphorylates the enzyme to bring about certain effects, and insulin, on the other hand, dephosphorylates the enzyme to bring about various effects. Therefore, when we phosphorylate the enzyme through our pKa subunit, the effect will be to increase your blood glucose level. But soon after this activation, our GTP and alpha subunit, they will break up. So what will happen of cyclic AMP? Our phosphodiesterase enzyme, well, subunit 3 and 4, comes in and breaks down cyclic AMP to 5' AMP so that this is not active anymore. This ultimately leads to stoppage of the activity of your receptors. Now another thing to note is that phosphodiesterase 5 enzyme, this acts on cyclic GMP and converts it into 5' GMP. One thing that you should remember is cyclic GMP is not a G protein coupled receptor. It is another type of receptor, which is your transmembrane enzyme linked receptor. So this was just for completion's sake, and once again, this is not a part of your G protein coupled receptor. Now let's look at the functions of your G inhibitory subunit. It is just the opposite of G stimulatory. That is, it will inhibit your adenylyl cyclase and therefore will inhibit the formation of cyclic AMP. The receptors which act through G inhibitory function are MAD2. What is MAD2? Muscarinic receptor 2, alpha 2, dopamine 2. These are the receptors which act through G inhibitory mechanism. Now next, let's look at our GQ subunit. This is another type of G protein coupled receptor. The effector in this is your IP3-DAG. In this, what your GTP alpha subunit does is it hydrolyzes your membrane PIP2 to generate IP3 and DAG. Now IP3 is water soluble, but DAG is not. So what does IP3 do? IP3 says, well, bye bye DAG, let me go inside the cytosol and bring about calcium. So it moves to the cytosol, mobilizes calcium from your smooth endoplasmic reticulum. Now DAG was obviously not going to be left behind. What it does is it activates your protein kinase C. Now the interesting thing to note here is it activates protein kinase C using the same calcium that IP3 released. So when protein kinase C is activated, it again phosphorylates various enzymes, transporters, ion channels, and brings about the various responses. Now that's all for this lecture. Thank you for watching the video. If you understood the lecture, please like, comment and share. Subscribe for more videos. Thank you.